What specific problem does the new method or algorithm aim to solve?
The new method, called Auto, aims to solve the problem of improving image quality in denoising diffusion models by separating the effects of prompt alignment and image quality improvement that are typically entangled in the existing classifier-free guidance, CFG method. Auto addresses the issue of skewed and oversimplified image compositions that result from the trajectory overshooting the desired conditional distribution in CFG. By using an inferior version of the main model as the guiding model with unchanged conditioning, Auto aims to guide the sampling process towards better image quality without the task discrepancy problem faced by CFG. Auto seeks to isolate the image quality improvement effect by utilizing a poorer model to steer the sampling trajectory towards more realistic and diverse image compositions.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method, called Auto, works by guiding a high-quality model, referred to as the main model, with a degraded version of itself, referred to as the guiding model. The guiding model is trained on the same task, conditioning, and data distribution as the main model, but suffers from certain degradations, such as low capacity and/or undertraining. This guiding process is aimed at improving image quality by addressing the limitations of the main model. The guiding model is obtained by limiting model capacity and/or training time. During sampling, the difference between the predictions of the main and guiding models is measured, and the guiding model's prediction is boosted towards the direction indicated by this difference. This process helps in pulling the samples closer to the data distribution without systematically dropping any part of it. By aligning the guiding model with the main model, Auto effectively improves image quality by focusing on regions where the main model may underfit, thus producing more realistic and high-quality images.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the proposed method, Auto, include improved image quality in image generation tasks. The method isolates the image quality improvement effect by guiding a high-quality model, with a poor model suffering from specific degradations, such as low capacity and/or undertraining. This approach helps in avoiding unrealistic and broken images by pulling samples towards the core of the data manifold and away from low probability regions, thus eliminating outliers and improving image composition. Auto also allows for better preservation of image style and visual complexity compared to traditional methods like classifier-free guidance, CFG, which tend to simplify the style and layout of generated images towards canonical depictions. Additionally, Auto can be applied to both conditional and unconditional models, leading to substantial improvements in image distribution metrics like FID and FDDINOV2, setting new records in image generation tasks. The method also provides a new artistic control by allowing the simultaneous use of multiple guiding models, offering a versatile approach to image synthesis. Furthermore, the method's adaptability to different network architectures, datasets, and training details makes it a promising avenue for future research in improving image generation tasks.
How is the method validated or tested?
The method is validated or tested by conducting a controlled experiment using synthetic corruptions applied to a well-trained real-world image diffusion model. The experiment involves creating a main model and a guiding model by applying different degrees of synthetic corruptions to the base model. The guiding model is constructed to have certain degradations, such as reduced capacity and/or shorter training time compared to the main model. By applying the proposed method called Auto, the impact of these degradations on image quality improvement is measured using metrics like FID. The results show that Auto largely undoes the damage caused by the corruptions when the degradations are compatible. Different combinations of degradations applied to the main and guiding models are tested to determine the effectiveness of the method. The study demonstrates that Auto improves image quality by guiding a high-quality model with a poor model suffering from specific degradations, leading to considerable improvements in image generation results.
What results were achieved with this new method?
The new method, called Auto, achieved significant improvements in image quality in various synthetic test cases and practical image synthesis settings, including class conditional and text conditional settings. The method was able to improve the generated image distributions considerably when measured using FID and FDDI-NOV2 metrics, setting new records in ImageNet 512 and ImageNet 64 generation. Specifically, using the small model EDM2S in ImageNet 512, the Auto method improved FID from a previous baseline to a new record. Furthermore, the method enabled unconditional synthesis, which resulted in substantial improvements in image quality, as indicated by lowered FID scores. The results demonstrated that Auto outperformed the concurrently proposed CFG plus guidance interval method and set new records in image generation quality, showcasing the effectiveness of the Auto method in improving image synthesis outcomes.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method proposed in the paper include the potential for distorted sampling trajectories, exaggerated truncation, mode dropping, and oversaturation of colors during image generation. Additionally, the method may lead to skewed and overly simplified image compositions due to the sampling trajectory overshooting the desired conditional distribution. Another drawback is the lack of separate control over prompt alignment and quality improvement effects, as they are intertwined in the method. Furthermore, the method relies on the assumption that the guiding model suffers from similar degradations as the main model, which may not always hold true in practical scenarios. Lastly, the method requires careful selection of hyperparameters, such as model capacity, training time, and weight values, to achieve optimal results, which can be a challenging and time-consuming process.
What future work do the authors suggest?
The authors suggest potential directions for future work, including formally proving the conditions that allow their method, Auto, to be beneficial, and deriving rules of thumb for selecting the best guiding model. They mention that their suggestion of using an early snapshot of a smaller model as a guiding model is easy to satisfy in principle, but note that such snapshots are not currently available for large-scale image generators. They also highlight that these generators are often trained in successive stages, potentially causing distribution shifts between snapshots that could violate their assumptions. The authors aim to explore how to make their method more widely applicable and effective in practical settings, considering the complexities of training large-scale image generators and potential distribution shifts during training.